All right, we're back. Strong versus weak acids. Now, what I mean by strong, I don't mean tissue burning, caustic. Okay, just there's another way to think about what a strong acid is versus a weak acid. Okay, so I have two acids here, hydrochloric, and you notice that acetate ions. That's acetic acid. All right, same concentration. So what I want to do is tell you what the pH of those solutions would be. All right, so the pH of this is 1.3, and the pH of this solution is 3.0. Okay, so you probably can tell right away which one's the strong acid. Right, that's the strong acid. That's the weak acid. Okay, so is that a surprise? Like, would you have been able to get that? So we know pH is equal to negative log concentration of hydronium ions. We know that. So, but that's the concentration of HCl. Okay, so let's use the Brownson-Lowry model and see how this will react with water. So when hydrochloric acid, a solution of hydrochloric acid, what'll happen is, okay, so we know Brownson-Lowry acids donate protons. So this is going to donate a proton. We're going to get hydronium ions in solution, and we'll get chloride ions, okay? Now, what strong acids do, they they donate all their hydrogen ions. So if this is 0.05 molar, this is also 0.05 molar, and this is also 0.05 molar. For every one of these, we'll get one of those. For every one of these, we'll get one of those. So that's where we got, so for a strong acid, the concentration of the acid is going to be the concentration of the hydronium ion. So if we plug in here negative log of 0.05, right? Well, you take the negative log. Oh, hold on. You take the negative log of 0.05. Guess what? You get 1.3. Okay? So strong acids, they donate all of their hydrogen ions. Okay? They dissociate completely. So if you have a solution, let's say you have a beaker, it's labeled 0.05 molar HCl, guess what? There's no hydrochloric acid, there's no HCl molecules in there. There's a lot of water, there's hydronium ions and chloride ions, and also some hydroxide ions, okay? Remember, we know that the concentration of this times the concentration of hydroxide is 1 times 10 to the negative 14th. There's not going to be a lot of hydroxide. So the label's a little deceiving, but it's a strong acid. Okay, so it's probably going to be important that we know what the strong acids are. There are 6 of them, the big 6 strong acids. Let me write these right here. So we know it's hydrochloric. I'm going to look at the periodic table. Hydrobromic, hydroiodic. Okay, and then we know it's nitric acid. I think you probably would have guessed that. That's another common acid. Use car batteries. Sulfuric acid. And then one more that's kind of out of the norm here. Perchloric acid. That's perchlorate, right? Perchloric acid. 1, 2, 3, 6. That's the big 6. Those are strong acids. If you're given the concentration of a strong acid, you just take the negative log to find the pH, okay? All right. So weak acids, they don't donate all their hydrogen ions. So this makes this calculation just a little bit more involved. So let's look at a weak acid. So this is strong. So let me erase, I'm gonna need all this space here. Let me erase this real quickly. Okay. Weak. Now, Just because it's weak doesn't mean it's not caustic. You know, hydrofluoric acid's weak, but it etches glass. So that certainly would do a number on your skin, right? Okay, so let's think about that weak acid. So we're doing now weak acid problems. So let's use all right. Let's use the Brownson-Lowry model. 2 plus water, and we're gonna get hydronium ions, of course. And then this acid, acetic acid, its conjugate base is the acetate ion. Now, let me clean this up a little more, okay? So we have some room here. We're gonna need some room. We're gonna need some room. All right. So, as you may have guessed, right? This acid will donate only some of its hydrogen ions. Weak acids donate only some of their hydrogen ions, okay? That makes it, that's what makes it weak. That's why the pH is greater. Less hydronium ions are going to be produced. So in a solution of acetic acid, we're going to have both of these ions, but we're also going to have some acetic acid. So when these guys bump into each other, the water just can't automatically take that hydrogen ion. All right, how do we do the calculation? We're going to need to know this. So for these kind of problems, by the way, I need to tell you, a reaction is reversible. So at the same rate these guys are getting together to form products, these guys are hitting each other and forming reactants. So we're said to be at equilibrium when that occurs. At equilibrium, when the rate at which the forward rate, equals the backward rate, okay, we're said to be at equilibrium. At equilibrium. So this is an equilibrium problem. Okay, so what we do with equilibrium problems, we set up what are called ICE tables. So ICE, or actually, let's say RICE. Reaction, ICE. Okay, I stands for initial, C stands for change, and E stands for equilibrium, okay? So, initially, we have 0.05 molar of this, and we have none of this and none of this, and we don't care about water, so we'll get back to that in a second. All right. So, you throw some acetic acid in 0.05. Initially, it's 0.05. It's not going to stay that way, though. I mean, this is going to donate some hydrogen ions, right? What's going to happen to this? This is going to decrease. By how much? We don't know. Let's just say minus X. Okay, so if this decreases, what's going to happen to each of these? They're going to increase, right? By how much? Well, for every one of these, we'll get one of these, plus X. And this will be plus X too. The coefficients are 1. For every one of these, you get one of these. For every one of these that donates a hydrogen ion, you'll get a hydronium ion, okay? And then at equilibrium, this will be 0.05 minus X. This will be X, and this will be X. All right. Next thing, we need to be able to teach, we have to teach you how to write equilibrium expressions. Equilibrium equation, equilibrium expression. So let me write right here, equilibrium expression. All you need to do is remember products over reactants. So Ka, K is a constant, A stands for acid, the acid dissociation constant, that's a fancy word for Ka, equals products over reactants. So it's going to be the concentration of hydronium ions times the concentration of acetate ions all over the concentration of the acetic acid. Now, what do you notice? We're not including water. Water's a liquid. So if we add some water to this, we're not going to change the concentration of this. We'll change the concentrations of these, because these are all aqueous. So the only things that are included in the equilibrium expression are aqueous and gases. So solids, no. Liquids, no. So this is our equilibrium expression, products over reactants, all right? Now, what we're going to do is we're going to throw this stuff into there. Now, I already looked up the Ka for this. The Ka for this acid is 1.8 times 10 to the negative fifth. And so we're going to let this is going to be X, this is X, and this is 0.05 minus X. So you see, we have X squared over 0.05 minus X equals 1.8 times 10 to the negative fifth. Well, that's quadratic, right? So, look, with your calculators, using the solver function makes it easy to solve quadratic formulas. But look, this isn't math class. We do enough math as it is. So we can make an approximation. Okay, think about this K. That is really tiny. So what that's going to say is not a lot of these are going to donate their hydrogen ions. So this is going to be a tiny value. So what we do is we let 0.05 minus X equal to 0.05. Look, X is going to be really tiny. Could be 0.00001. So if you subtract 0.05 minus 0.00001, it's basically 0.05. So this is referred to as a little x problem. And so we just do this. We just get rid of it. And then we solve for x. Okay? So let me just use my calculator here. I'm going to cross multiply. I'm just going to multiply both sides by 0.05 and then take the square root. And we'll see. I'm sorry, I'm kind of running out of room here. Times 1.8 exponent negative 5 equals, take the square root. Yeah, I should write all this down for you. So x squared equals 9 times 10 to the negative 7th. So x equals, take the square root of that. So it's 9.5 times 10 to the negative 4th. Okay? Yeah, so what's x? X is this, right? So now we know the concentration of hydronium ions. So now we can figure out the pH. So pH equals negative log of 9.5 times 10 to the negative 4th, and I'm hoping it's 3.0, and it's going to be really close to negative 3. Yeah, because this is close to 10, so 10 times 10 to the negative 4th is 10 to the negative 3rd, and we know that the negative log of 10 to the negative 3rd is 3, so we know this is 3.0. Okay, I'm just rounding off. That's the pH. Okay, strong versus weak acids. So, strong acids dissociate completely, donate all their hydrogen ions. To find the pH of a strong acid, just take the negative log of the concentration. To find the pH of a weak acid, there's more involved, right? There's making an ice table or a rice table, reaction, initial, change, equilibrium, writing the expression, plugging this equilibrium line into the expression and solving for x. Okay? It's possible that we could change these problems around a little bit. I could give you the pH and you can figure out Ka. So we'll have to, I think I'll make another video where we do that, where I give you the pH and you have to figure out what Ka is. We'll do that next. Okay, this has been long enough. So, introduction to strong versus weak.